Thank you very much. Thank you very much for the invitation. I'm quite honored to be in India for the first time. And I really appreciate the effort of putting this together. Manoj is there. So thank you for the conference. Okay, I'm going to talk about Silo subgroups and character tables. And let me tell you that one of the main themes in representation theory these days is the connection between global and local. So global is that I will have a finite group G. And I have the set of irreducible characters of G. This is the global part. So I'm going to fix a prime P. And in the most basic situation, I'm concerned about Silo P subgroup. And the local part are P subgroups, the most important P subgroup, and also normalizers of P subgroups. The most important one is the Silo normalizer. I can make this more sophisticated by talking about blocks, about defect groups, but I'm going to stick to the most basic case. The most basic case, I'm going to have the character table of G. And of course, the character table of G, as we know, determines many of the structure of G, such sizes of centralizers. It's very easy, or even the order of the group. Even this is more complicated. The primes dividing the order of the elements, not the order of the elements, as we know. This is a theorem of Hickman. We know if G is solvable or simple, nilpotent. We know the size of the fitting. So all this is pretty easy. But if we want to go and know about the local properties, that is much more sophisticated. Okay, for those of you that have heard this talk in other parts of the world, I mean, I apologize, but I do have something new. So. Okay, so I have divided my talk into two parts. One is A, which is before Mackay. And the analogy before Mackay, after Mackay, is not, I don't think it's very good, because before Mackay, we had no less than Richard Brouwer and problem 12. And Brouwer asked, if you know the character table X of G, how much do you know about P? He asked for is, can we detect if P is abelian? This problem was solved in 1995 by Wolfgang Kimmerle and Robert Sandling. In the following way, they proved that if xg equals xh, and G has abelian Silo P subgroups, then they proved that H also has abelian Silo P subgroups. But this is not a practical method. I mean, Brouwer was not thinking on this solution, I think. He was thinking on the following, on the so-called Brouwer's high zero conjecture. I'm going to state it only for, I mean, without using blocks. So I'm going to state it just for those of you that know blocks, for the principal block. And it says the following, that P is abelian if and only if, whenever this sum is not zero, for chi an irreducible character of G. Of course, you can detect that in the character table. You can compute that. Then P doesn't divide the degree of the character. Okay, the conjecture in this direction, not only for the principal block, but for every block, is an impressive theorem by Prada, Kessar. So this direction is now complete. It's Prada, Kessar, and Gunther Mahler. And this direction has been reduced. This is work by myself. T is going to stand for Tiep in this talk. And Brita, sorry, so she has to come first. Speth, Brita Speth. By work of us, now this is a question on simple groups. Okay, if you look at Brouwer's paper, I mean, there is a wonderful paper by Brouwer in which he asks about all these questions. Then he numbers the questions, but there is some place in the paper, there is not a numbered question in which he asks something which is much easier than this. If you care about P abelian, I mean, if you have a group which has a abelian Sylopi subgroup, then every P element lies in some Sylopi subgroup, so you know that if X is a P element, let me call this condition star. So if X is a P element, then if the Sylopi subgroup is abelian, then do you know that this number is not divisible by P? Right, because P is in the centralizer. So Brouwer in that paper asked whether or not this condition, let me call you star star, was characterized in abelian Sylopi subgroups. That's much easier than this one, or much easier. Looks easier. Okay. But Brouwer, in that time, he didn't know about these groups. I think it's J4 and root valleys. These are counterexamples for P equals 3. And there is one also for P equals 5, which is the Thomson group. In the positive, for P equals 2, this was true, and this is a theorem by Kamina and Herzog. And after seeing this, we tried for what is going on for P bigger than 5, and we were able to prove that for this is myself and Tiep, for P bigger than 5, also true. So putting all this together, we were able to show this is a theorem with myself and Ron Solomon and Tiep. We were classifying the groups in which this doesn't happen, and by using this classification, we showed that P is abelian. If and only if star plus 2 star. Eventually, Brouwer's high-zero conjecture is going to be proved, we hope, so it will be just 1 star. But still it's a long time until Brouwer's high-zero conjecture is proved, I think, in the other direction. Okay, I know that young people always look for problems, and they have a problem, which I think it's crazy, but I haven't found any counterexample. So Brouwer was asking about if the character table knows if the Sylopi subgroup is abelian. I'm asking if the first column of the character table is enough. I know this sounds crazy, but I haven't found any counterexample, so let me not say conjecture, but a problem. The first column of the character table is just degrees and multiplicities of degrees, so I'm wondering if C of G determines if P is abelian. And I'm also wondering, once you have done the P abelian case, I would love to see this number in the character table. P prime is going to stand for the right subgroup of P. So in order to prove that, you have to find two groups with the same character table and different sizes. I don't know. Okay, so now we go to my second part, which is after Mackay. Yes? Oh, sorry. Excuse me. Double star means this condition. Double star means that for whenever you have a p element, then this is not divisible by p. In the character table, you can detect p elements, and then you do the second orthogonality relation, you calculate these numbers, and if this is not divisible by p, then if p is not 3 and 5, the single p subgroup is going to be a billion. If p is 3 and 5, then there are examples. Okay, sorry, I didn't hear you. I think this is complicating me a little. So this is after Mackay. Well, we have heard the name John Mackay here a couple of times. And I mean, he's an amazing mathematician that he sees things. This is also important. Well, it's very important. And aside of the moonshine that we heard about, I mean, he just saw something. And this is the Mackay conjecture that says that if it's a finite group, Mackay conjecture. That says that if G is a finite group and P is a prime, this is going to be the number of irreducible characters of G that have degree not divisible by P. P prime means P prime degree. So he observed that this was true in the groups that he checked, that this equality was true. And this is what makes you love mathematics. I mean, two different groups, something unexpected, something deep. In fact, I mean, he only realized that this was happening for p equals 2 and for simple groups. But this became known as the Mackay conjecture. I'm not going to talk today about Mackay conjecture, but about consequences of something deeper. But I cannot resist mentioning that in 2007, we reduced this. This was Isaac's, myself, Male and myself, we reduced this to a difficult question on simple groups. We didn't reduce the problem to simple groups. We reduced it to a question on simple groups, very sophisticated question. And then in 2015, Gunther, Male, and Britta Speth, they proved the case p equals 2, which was the original case. So this is a success in the sense that the path that we started now has concluded, at least for p equals 2. What's going to happen for p odd? I mean, this is not my business anymore. It's business for the simple group people, but they are confident that it's looking good, so perhaps in some years. Okay, so Mackay is about two sets that are simply, that there is a bijection between them. So after thinking a lot, we came thinking about some possible generalizations, and I'm going to talk about consequences of one of those generalizations. So Mackay simply says that there is a bijection. So in order to understand Mackay, we started thinking on possible variations of this, not just for the sake of generalizing, but just to try to understand what was behind. So now there is something for blocks, which is called Alprin-Mackay. So height 0 characters of Brouwer-Fersman correspondence. There is also about congruences of degrees that I discovered with Isaacs. There is also something about the automorphism group that stabilizes P, permutes these sets isomorphically. That is also very impressive, very interesting. All these are conjectures that help us to understand what's going on. But the conjecture I want to tell you about today is a version that I did with Galois action. So I'm going to call, I can call about the absolute Galois group, but let me just mention. Let me work with this one. So for the purposes of this talk, this is cyclotomic, Q, some root of unity, primitive root of unity. And then it is false that, this Galois group acts on characters. It is false that there can be bijection commuting with this action. It is false that that these two sets have always the same number of rational characters. This is totally false. But this was not natural to expect that, because here we have a prime P. So what I conjectured was that the action of GP, this is just the Galois elements that send a prime ideal containing P of the ring of algebraic integers inside here to itself, the ones that stabilize the P, then the actions of GP on both sides are isomorphic. So if this conjecture is true, and we are very, very, very far from proving it, then this implies that there is an intimate collection, an intimate relationship between character values, not only about these numbers, but about the values. And I'm going to show you some consequences that we have proved. So these are not going to be conjectures anymore, but theorems. Okay, for instance, by elementary character theory, this set it's simply the characters of this group. So this group now is in the center of things. So this section of the group is important. And this is just P prime acted on by the normalizer of P mod P. So as you can see, this group shows up again, P mod P prime. This is why I think it's important. Okay, so my first objective when I tried to understand what was going on with the Mackay conjecture was what can I prove it when this is 1? So I was interested in the case when the normalizer of P is P. And I succeeded in proving that for P odd and for P equals 2. Now we know that everything is true. But let me tell you what interests, some consequences of all that work in the character table. Okay? So can we detect this in the character table? And the answer is yes. There is a theorem, but this is only for P odd. This is a theorem of myself and Thiep and Tulul that says the following. Okay, I want to detect this condition in the character table. So you give me these numbers, and I want to tell you if the normalizer if the CILO is normalizing or not. How can you do that? And here is the way, and this is a consequence of this conjecture. But this is a theorem. We have proved that. And the consequence is that the normalizer of P equals P, if and only if the only P prime degree, I will explain later, P rational character of G is the identity. P rational, a character is P rational if the field of values lie in some cyclotomic field where P doesn't divide N. So a character chi is P rational if this happens. Okay, so now you go to your character table, you can check P rationality and degrees, and now if there is only one, if and only if the CILO P is still normalizing. Okay, this only happens for P odd, and there is a version for P equals 2 that is wide open. So there is a difference between Mackay conjecture and the Galois version. I mean, for p equals 2, now we know that this is true. But however, we don't know, for instance, about there is a similar statement for p equals 2, but right now it's not possible to do it, because right now it's not known how the Galois group acts on the characters of the simple groups. Okay, so the next step when you are interested in local, global, the next step is when for local, global stuff, the next step was to decide if this group has a normal, when this group has a normal p comparator. In block theory, local group theory, having a normal p complement is the most natural condition. This has been later generalized to blocks and with nilpotent blocks, etc. So this was very natural to us. And again, after I thought on this for many years, and suddenly we saw a way of doing this, which is also very natural. And this is a theorem by myself, Piep, and my former student, Vallejo. And again, for p odd, we proved that the normalizer of P has a normal P complement. If and only if it's similar, but I only need to go to the characters in the principal block. The principal block are the characters in the condition star that I wrote before. For p equals 2, we have a similar statement that follows from the Galois-Mackay conjecture, but it's impossible. This was for us the beginning of something. I said that I was not going to talk a lot about blocks, but let me mention that one of the big problems in representation is, I mean, we have a block of G, and we have the Brouwer first main correspondent, the normalizer of some defect group, and these are algebras, and we want to know exactly what is the relationship between these two algebras. And a key case, I think, is to decide to talk or to characterize when L of B equals 1 from the point of view of B. And this takes care for the principal blocks. Having a normal P complement by a theorem of Brouwer is the same as having a unique Brouwer character. I'm not going to, L of B means the number of Brouwer characters in the block. So let me let this thing here. Okay, problems about this. I have a problem that some people is thinking of. So the character table, does the character table determine the number of Sylow-P subgroups? Or, in other words, does it determine the size of the normalizer? We have been thinking on this problem for a while, and if you just go to the first interesting case, it's already a very difficult case. First interesting case is when the group G, again, has a normal P complement. So normal P complement, I didn't say it. Normal P complement is that you have a normal P prime subgroup with index a power of P. Okay, so imagine that you have a tiny group like this, okay, and you want to know, you know the character table, you want to know the size of the normalizer. Well, the normalizer lives here, and when you go down, what you have is the fixed point subgroup. So in this tiny case, what you want to know from the character table is the size of this, the size of the fixed points. Okay, we were lucky, very lucky to find this theorem. If you're thinking on this for a while, you realize, for instance, that the P is C2 cross C2. Then there is a famous formula by Richard Brouwer that tells you what is the size of the fixed point in terms of the size of the involutions. And we wanted something similar. And here is the formula that we found. So this is joint work with myself and my student, Noelia Risto. So we found the following formula. I'll explain later. And the formula is this one. If P acts on K, etc. So the size of the fixed points is the product X in P of the centralizer of Kx, centralizer of Kx to the P, 1 to the P, and all this raised to P minus 1, P. If you plug this formula for C2 cross C2, you get Brouwer's formula. And also this also generalizes a formula by Wieland. How on earth we arrived to this formula? That's a long story, because it took us months. My student was doing many, many particular cases. And I think it was my last moment of really seeing things. I saw this formula somehow. And afterwards, when you see the formula, proving it, I mean, it's not easy, but it's not that difficult either. You do it by induction, you use some tricks, and everything is okay. But the most important thing was to find the formula. And the formula is working. Once you have this, it's not trivial to go from P solvable to this case, but there are some fusion theorems that you can apply. And so the corollary is if G is P solvable, and you know XG, and we need the P power map. P power map is the P powers. Then this determines the size of the normalizer. We don't know how to erase this condition, but this is a classic condition. We don't mind too much. I mean, if you read Brouwer's paper, Brouwer was also asking about character table determines this, or character table plus P power map. That's a classic condition, so it's okay. But still, we would like to delete that, but we don't know. Okay. Yes, this is a P group that acts whenever you have a P group that acts on a P prime group. Then the size of the fixed points is given by this formula. Okay, so now I'm going to go to the other part. Okay. So I have been more interested in the size of the normalizer. Now I'm going to go to the other section, which is this section. So now I'm interested in P mod P prime. As I said before, I would love to know if the size of this group is in the character table. We don't know that. But what we have found is the following. This was a joint work that I had with Isaacs, and this was the origin of the Mackay-Galois. It's about a tiny little Galois automorphism, and this is the following. So I'm going to, for every E bigger than or equal to 0, I'm going to define sigma E, and this is a Galois automorphism. I can define it, I mean, I'm going to define it just for cyclotomic fields of some roots of unity. So it's gonna do the following. So it's going to do this on P power roots of unity. And is going to fix P prime roots of unity. This is one of my Galois automorphisms. If you, doing some little number theory, then you can check that this automorphism fixes the prime ideals containing P. So, this sigma belongs to this group. So I can play with this sigma. So in a paper with Isaacs, we realized that something was going on. And it was the following. And this is very much into what worries me about this kind of problems. It reflects my interest here. So this was a conjecture by myself and Isaacs. Before stating the conjecture, let me show what this Galois automorphism does to linear characters. So suppose that you have a linear character of a P group. When is it fixed by sigma E? Well, you can check easily that lambda sigma E is lambda 1 P to the E. When this is fixed? Well, this is fixed if and only if lambda P to the E equals 1. So if and only if the order of lambda divides P to the E. Now you would understand better our conjecture. So our conjecture says that the exponent of P prime is less than or equal to P to the E if and only if all characters of P prime degree are sigma E fixed. This expresses very well, I think, the kind of problems that we are facing. Look at this. This part is very global. It's global. You can check this in the character table. And suddenly this gives you information on this important section of the group. I find even more amazing the other part. Because, you can have many groups with the same P mod P prime. And it's telling you that all the characters are going to be fixed. So your group G is very far from the Silo P subgroup, and still there is this connection. Okay, so let me give you some news about this. The news about this is that, okay, so now this is conjecture, and this was the origin of my Mackay-Galois conjecture, but this is a theorem, and the theorem says that this implication, now this is myself and here, this implication is true. We have proved this, and the other implication, we have reduced it to almost simple groups. Not to something complicated, an almost simple group. Well, it's complicated enough, but it's the same statement. As I said before, the reduction of Mackay was not about, if you prove Mackay for simple groups, then you have Mackay in general. No, it's something more complicated. In this case, it's the same thing, to reduce to almost simple groups. Okay, I'm a little bit of hiding the deep part of the deepest part of what I'm saying. And let me just show how can you prove something like that? And then I will stop exactly at the point where my colleague Diep is taking these things. And he's taking these things in the most complicated step. It's when he has a simple group and he has to prove these things for simple groups. which is very complicated. Because as I will mention later, for alternating groups, everything is more or less, these theorems work nicely, they're not that difficult, but for groups of Lie type, not an expert, but it seems that the characters are parameterized by something that is not canonical. And suddenly, if you have that, then you cannot control Galois actions or automorphism actions. It's very difficult. So an open problem right now is how the automorphism group of a simple group acts on its character. An open problem is how the absolute Galois group acts on the reducible characters of simple groups. That is open. So just in the 4 minutes, let me tell you how to prove these kind of things. So I'm trying to prove. I'm not going to do just a very sketch. So how do you prove that? So you know that the characters, we know are sigma fixed. We want that the linear characters of P are sigma fixed. This is what you want to prove. So how do you go from G to P? That's a long way. Okay, what we usually do in group theory is do induction, and this starts the thing. So you take a minimal normal subgroup, and then by induction, you know that the linear characters of Pk over K are sigma fixed. So this is when you say, oh, if K is a P prime group, I'm done. Okay, yes. If K is a P group, that's an exercise for you. Not trivial, but I mean, it's nice character theory, but it's not a triviality. So, okay, so I do these two things, and then I may assume I try to approach as much as possible to TIEP, and TIEP is about simple groups. So now I take care of these two cases, and I say, well, so K is a direct product of simple groups. But still you are very far. I mean, you want to go as closer to P as possible. And the trick, and this is not that trivial, the trick is to show that Kp satisfies your hypothesis. How do I know that? Well, because I have to believe in my conjecture. If my conjecture is true, it goes both ways. So if my conjecture is true, G will know about P, and P will know about Kp. So Kp will have the same condition again. So once you know that, once you believe in your conjecture, then it's a matter of technicalities. I mean, how to go from here to here. And it's not easy, but with character theory you can do it. But there are a couple of things that are important. Is when you have P prime character degrees, the restriction is irreducible. Still, you're very far from G. But there is something that is nice, and it's, well, you have theta you can induce, and because this is P prime, you have a P prime character here. Right? I mean, this index is P prime, so by counting, theta is a P prime character, so you start with a P prime character. You want that theta is sigma invariant. So you go up to chi. Now you know that chi is sigma invariant by hypothesis. And then, I only have 30 seconds because Gerhard told me that I have to stop at 45. So now the trick is, okay, so chi is sigma fixed. And now how I go back? Well, because the sigma, it's an easy exercise, has order P power. Those automorphisms have order P power. So by counting, when you restrict, you have here some character theta 1 that is sigma fixed of P prime degree. This is counting, nothing deep here. This is sigma fixed of P power degree, of P prime degree. You restrict, you have to have some by orbits. But now, theta 1 restricts to some conjugate. You may assume that it's the same. So now I'm very close because now that theta 1 and theta, they are both extensions of something that is sigma fixed. But there is a theorem that says that you can extend this canonically. So in the end, these two are just, by Gallagher's theorem, they differ by a linear character. But I know by induction that these characters are sigma invariant, so I'm done. I rise a little bit here, but if you want to check the details, I mean, everything is working. So I stop here for the discussion.
For this nice talk. So I open the discussion.
Easy discussion.
So this chi in your reduction, this is the induced character or an irreducible constituent of the
induced. Irreducible. You induced. Yeah, you induced. And this has p prime degree. Some irreducible constituent has to have p prime degree. And the same trick happens when you restrict, but now with the sigma invariant thing. Please. This conjecture over there. Yeah, the Galois version. Oh, this. Yeah, that's a very good question. When do you know that a conjecture is going to be true? Well, I mean, there is a say by John Alperin that we respect him a lot, and he says that if you have a conjecture which you have verified for solvable groups, GL, symmetric groups, and sporadic groups, then you are safe. In this paper, we checked this for solvable groups, for p-solvable groups. For symmetric groups, should be everything is sigma fixed, so that should be easy, I guess. Right? I mean, you just take the symmetric groups; they satisfy this, and we asked probably someone for GL, and we checked in the atlas. With some, I mean, you check it easily in the atlas, and suddenly we didn't know. I mean, when we conjectured this, we didn't know about this. But when you realize, when you think about it, this is the right group to be acting on Mackay, and suddenly everything fits together. You are confident that it's going to work. But of course, we don't know.
Okay, are there more contributions?
For groups of Lie type, this should be wide open in one direction. I mean, in this direction, Dieppe has checked it because the conjecture is true. In the other direction, I don't think. And we have an expert, another expert.
So in this particular case where you reduce it to Kp, is that right? You reduce it to Kp, yes. But then you have to prove something about finite simple groups or quasi-simple groups.
Yes, I skipped that part, thank you. I mean, now it's direct product of simple groups times a P, but I still have to reduce. Now it's not so complicated to go to one of the factors times something that normalizes. You have, it's very technical, but it's possible. So from Kp to S, the normalizer in P of S, then it's doable. It's pages, but it's not that complicated. And then you have simple group acted on by a P group. And then you are in Dieppe's territory or in your territory. I mean,
but you still have to prove something about the sigma E fixed. You have to show, I mean, you have to produce the characters that are sigma E fixed.
Yes, totally. This is Dieppe's job.
Okay. Okay.
So, but yeah, yeah. When I arrived there, I said, "Yep, now it's your turn."
More questions or, yeah, please.
Yeah, you just have to, yes. Well, you need to know all almost simple groups. You have to do it for all of them. I'm leaving my colleague a lot of work. So, oh, sorry. Oh, sorry, I didn't understand you. I don't think so, because there is a lot of subsections. Yeah, that was a good question. Sorry, I misunderstood. Yes, you need, here, for instance, we are working on, in order to do this kind of things, to do things over a character of some normal, I'm stating things as easy as possible. You have to do this over some normal subgroup. Then you have an stabilizer, so it's a subgroup. So then you need to know the composition factors of the subgroups. So by induction, in the end, it's hard to keep track of. Usually there is always a nice consequence of these things, is when for instance, you say that, that the CLO2 is a billion, for instance. Then you know that the composition factors of the subgroups are all the same type, and then you can show the strength of your methods proving this case. But in general, you cannot say, okay, so if it's true, if I prove for simple groups for these families, then I know for these groups. No, that's very complicated.
Okay, I don't see any more contributions, so let's thank Gabriel again.
Okay, thank you.